Hello, welcome to the another lecture of control system and instrumentation. I am Mr. Prajit from Asansol Engineering College. Like to giving you some discussions about the stability of a given system, how to determine stability of the given system. I already discussed several things about the fundamental knowledges of control system and instrumentation from lecture 1 to lecture 7 respectively, where I already mentioned how to determine transfer function, and depending on transfer function with the help of block diagram reduction method, how can I evaluate with the help of block diagram algebra application, how to evaluate the transfer function with the help of block diagram reduction techniques. Even I mentioned signal flow graph based on Mason's gain formula, how to evaluate transfer function from the electrical circuit, mechanical circuit, electromechanical system. Even I discussed about the analogous systems also. Analogous system is nothing, that means suppose I am providing a mechanical system and what will be the electrical equivalent circuit for the same, that is also analyzed. And today ensuing slide will be discussed on the stability concept, how to determine stability. See, a system is said to be stable if its output is under control, otherwise it is said to be unstable. Obviously, a stable system produces a bounded output for a given bounded input, and that's acceptable. Now, the types of stability based on system is, that is, we can classify the systems based on stability as: number one is absolutely stable system, then conditionally stable system, marginally stable system. So what are the absolutely stable system and what are the relevant conditions for the same, that should be known to you. So if the system is stable for all the range of system component values, then it is known as the absolutely stable system. The open loop control system is absolutely stable if all the poles of the open loop transfer function present, yes, in the left half of S plane. Yes, S plane is nothing, that is sigma plus j omega. Sigma is along plus minus sigma is along x axis and plus minus j omega is along y axis. That is the scenario. So similarly, the closed loop control system is absolutely stable if all the poles of the closed loop transfer function present in the left half of the S plane, then we can speak. Okay, now conditionally stable if the system is stable for a certain range of system component values. If the system is stable for a certain range of system component values, then it is known as conditionally stable system. Yes, and if I am looking this conditionally stable system in S plane or sigma and j omega plane, j omega axis, so if my poles are lying on the imaginary axis, then we can tell, that means, that is the condition means, see, actually after that the system can become from stable mode to the unstable mode. So that's why it is known as the conditionally stable system. That means if I am providing some gain parameter, yes, if I am providing some gain parameter k, and that is to be valid for the ranging value of k, because under certain limits of k that system will become stable, else it will become unstable. So that is known as the conditionally stable system. And marginally stable is nothing, that is, if the system is stable by producing an output signal with constant amplitude and constant frequency of oscillations, yes, for bounded input, then it is known as marginally stable system. So in this scenario, the open loop control system is marginally stable if any two poles of the open loop transfer function is present on the imaginary axis. Yes, that is the scenario. That means imaginary axis means if any poles lying on the plus minus j omega axis, parallelly there has no pole lying on the right half of S plane, but any pole can lying on the left half of S plane, then we can speak that system is marginally stable and the nature of the response is sinusoidal, that means oscillatory. That should be in your mind. So similarly, the closed loop control system is marginally stable if any two poles of the closed loop transfer function is present on the imaginary axis. So these are the fundamental bases for the nature of stability, and you should have a sufficient concept regarding that. And one thing I need to speak, for perfectly stable system, that means if no poles lying on the right half of a plane but any pole lying on the left half of a plane, or all poles lying on the left half of a plane, then the nature of the response is exponentially decaying nature. Whereas if any pole lying on the right half of a plane, then the nature of the, that means system is become unstable and the nature of the response is exponentially rising nature. And similarly, any pole lying on the imaginary axis but no pole lying on the right half of his plane, then we can speak that system is in oscillatory nature, that is sinusoidal. Okay, now we are entering to the absolutely stable system determination, is known as the Routh-Hurwitz or RH criterion. A stable system is a dynamic system with a bounded response to a bounded input. And consider the closed loop transfer function of a system given as T of S is equal to Bm s to the power m plus Bm minus 1 s to the power m minus 1 plus 1 dot 8 B0 divided by An s to the power n plus An minus 1 s to the power n minus 1 plus 1 dot 8 A0 is equal to n of s by delta of s. N of s is nothing, that is polynomial at the numerator, and delta of s is nothing, that is polynomial at the denominator. Now the characteristic equation or polynomial of the system is given by, that is delta of s is equal to q of s is equal to an s to the power n plus an minus 1 s to the power n minus 1 plus 1 dot 8 plus a0. Now for the system described above by T of s to be stable, the roots of the characteristic equation must lie in the left half plane. Just now I told you people based on the S plane concept. The Routh-Hurwitz criteria or test is a numerical procedure for determining the number of right half plane, that is RHP, and imaginary axis roots of the characteristic polynomials. Now, Routh-Hurwitz method stability criteria. The method requires two steps. Step 1, generate a data table called a Routh table or Routh array as follows, where the characteristic equation to be considered, that is delta of s is equal to q of s is equal to, for example, we are providing a4 s to the power 4 plus a3 s cube plus a2 s square plus a1 s plus a to the power 0 a0 a1 s to s plus a0 s to the power 0. This is the respective example. Now our first job, if we are looking to the right side diagram, there see we are starting from the higher order or higher power of s in the descending order. We will fill it up the table in column-wise, that is s to the power 4 starting from s to the s cube, s to s square, s to the power 1 and s to the power 0 should be mentioned. Then first row, that is s to the power row, should contain the alternate coefficients of the respective characteristic equation. Starting from here is a4 a2 a0. See, I have written a4 a2 a0. The next row will be substituted as the rest coefficient in an alternative nature, that is a3 a1 and nothing is there, that's why 0. Then s2 should be filled up with the respective multiplication rule, cross multiplication rule, that will be analyzed afterwards. Now then s to the power 1 and s to the power 0 will be filled up. So rules for Routh table creation is, any row of the Routh table can be multiplied by a positive constant without changing the values of the rows below. Yes. To avoid the division by 0, and epsilon is assigned to replace the 0 in the first column. So this is the problematic analysis, and after doing lots of problem, the relevant things, the relevant key things with respect to RH criteria is to be very much clear to you people, because RH criteria is highly essential when you will sketch root-locus graph. That is to be known to you, because when root-locus intersects imaginary axis, you should have to take help from the concept of RH criteria. Now, how can we fill the rest elements of the Routh table or Routh array? See, already the same problem is going on. Again, I am repeating the same. S to the power 4 row contains the alternate coefficients, that's a4 a2 a0. S cube row contains a3 a1 0. Then s to the power 2 contains the restricted ordered cross multiplication, that is minus of determinant A4 A2 then A3 A1 divided by A3, that generates B1. Similarly, the second element for the S2, that is second column element with respect to S2, S to the power 2 is minus of determinant A4 A0 according to row wise, then next row will be A3 0 divided by A3, that is B2, and then another element for it will be minus of determinant A4 0 then A3 0 divided by A3, that is nothing, that is 0. And subsequently for S to the power 1 row is nothing, that is minus of determinant A3 A1 then B1 B2 determinant, within that determinant divided by B1, that generates C1. Similarly, for the second element, it will be minus of determinant A3 0 B1 0 divided by B1, that is 0, and rest element is also 0 for the S to the power 1 row. And for S to the power 0 row, the first element of the column is minus of determinant B1 B2 according to row wise, then C1 0 divided by C1 is equal to D1. Similarly, the next element will be minus of determinant B1 0 C1 0 divided by C1 is equal to 0, and another element is also 0. Then we can speak our route table is filled up or completed. This is the nature of the multiplication, but you should not violate this one, okay? Otherwise you can generate the wrong result. Now here see the stability criteria mentions step to interpret the route table to tell how many closed loop system poles are in the left half plane, that is LHP, or right half plane, that is RHP. The number of roots of the polynomial that are in the right half plane is equal to the number of sign changes in the first column. Yes, very important thing. That is, again I am repeating, the number of roots of the polynomial that are in the right half plane is equal to the number of sign changes in the first column. And what are the relevant notes for that? Number 1, if the coefficient of the characteristic equation have different algebraic, there is at least one right half plane root. For example, delta of s, that is polynomial, that is the denominator polynomial is q of s is 7s to the power 5 plus 5s to the power 4 minus 3s cube minus 2s square plus s plus 10. Obviously sign changes have been made, that's why we can speak for this example at least one root will lie on the RHP and system will become unstable. That thing we will see. How can I tell unstable? So has definitely one or more right half plane roots. Similarly, if one or more of the coefficients of the characteristic equations have 0 value, there are imaginary or right half plane roots or both. For example, if the polynomial is characteristic polynomial is delta of s is equal to q of s is equal to s to the power 6 plus 3s to the power 5 plus 2s to the power 4 plus 8s square plus 3s plus 17. In this scenario, see, all the power of s is available except s cube. That means 0 is to be 0. The s cube means we have to introduce the 0 coefficient for s cube, because s cube element is missing. So on that occasion we can speak there has imaginary axis roots indicating the missing term. That should be known. Now, necessary condition for route-Harvey stability. The necessary condition is that the coefficients of the characteristic polynomials should be positive. This implies that all the roots of the characteristic equation should have negative real parts. Yes. Consider the characteristic equation of the order n, that is a0 s to the power n plus a1 s to the power n minus 1 plus a2 s to the power n minus 2 plus so on dot an minus 1 s plus an s to the power 0 is equal to 0, provided a0 is greater than 0. Note that there should not be any term missing in the nth order characteristic equation. This means that the nth order characteristic equation should not have any coefficient that is of 0 value. What is the sufficient condition for RH stability or route-Harvey stability? The sufficient condition is that all the elements of the first column of the route array should have the same sign. Same sign means obviously positive sign, not negative. This means that all the elements of the first column of the route array should be positive. Okay. Now we are directly coming to the problem. For the system shown in the figure 1, determine the transfer function T of s and then apply the route-Harvey's method to check the stability. So obviously the forward path transfer function is provided, that is 1000 by s plus 2 into s plus 3 into s plus 5, and the order of the system is third order type 0 system. So what? So already we know with the help of block diagram reduction technique what is the total transfer function. Negative feedback is available. That's why T of s is equal to G of s by 1 plus G of s H of s. And then after substitution we are generating 1000 by s cube plus 10s square plus 31s plus 1030. So this is the characteristic polynomial s cube plus 10s square plus 31s plus 1030. Then we have to construct the Routh table for this characteristic polynomial. So starting from the higher power of s is s cube, then s square plus s to the power 1, then s to the power 0. Then alternate coefficients should be substituted on the very first two rows, that is 1, 31 first two row, then 0 is unless it will come obviously, and then another is 10, 1030. That means I am taking common 10. You can keep 10 also, no problem. When I am taking common 10, it generates 1 and 103. Otherwise it will, you just keep it 10 and 1030. It does not bother any problem. So with the help of the restricted cross multiplication, whatever things I discussed on the previous slides, I am generating the s to the power 1 row. First column is minus 72 and the second column is 0, third column is obviously 0, and s to the power 0 is, that is 103, and the second column is 0. And one thing I need to speak about s to the power 0, see here, after taking common of 10 on the s to the power 2 row, we are making 10 is 1 and 1030 is 103. If you are left, if you are not at all taking common 10, then it will be remaining 1030. So s to the power 0 row contains the first column element is 1030. My intention is, what I am speaking, after fulfilling all the elements of the Routh table, you should check your S0 row of the first column must contain the last coefficient that of the S0. That means here see 1030 is there, that should be available. I am taking common 10, that's okay, but it should be available. Otherwise your Routh criteria fulfilling is totally wrong. That is the intention. So in this occurrence, if I am looking to the first column of the Routh array, two sign changes have occurred. See, from s square row to s to the power 1 row, 1 to minus 72, positive to negative, and s to the power 1 row to s to the power 0 row, then minus 72 to 103. So there are two sign changes in the left column. Therefore the system is unstable and has two roots in the right half side or right hand side or right half plane. Now another problem. Apply the Routh-Hurwitz method to determine the stability of the closed loop system whose transfer function is given by T of s is equal to 10 by 3s to the power 5 plus 5s to the power 4 plus 6x cube plus 3s square plus 2s plus 1. Obviously, with the help of the concept for Routh-Hurwitz table, we can construct it. That is, starting from the higher power of s is s to the power 5 to s to the power 0. Then alternate coefficient will be substituted on the very first two rows. That is 3, 6, 2 will be substituted on first rows. Then 5, 3, 1 will be substituted on the second row. Then s cube row contains the elements are generating 4.2 and 1.4 after restricted cross multiplication. You can verify the same. S to the power 2 row contains 1.33 and 1 respectively. S to the power 1 is contain minus 1.75. S to the power 0 is contain 1. See here, coefficient of s to the power 0 is 1, whereas the polynomial contains the coefficient of s to the power 0, that is see 3s to the power 5 plus 5s to the power 4 plus 6s cube plus 3s square plus 2s plus 1 into s to the power 0. I am speaking that thing. So that value is available at the s to the power 0 row. So that's why we can speak the Routh table is fully correct. Now our next job, we will determine the stability. When I am focusing to the first column of the Routh array that contains one negative sign, that means two sign changes have occurred, that is 1.32 to minus 1.75 and minus 1.75 to plus 1. That's why we can speak that system is unstable and two roots lying on the right hand side of the S plane. So that should be known to you people. Very easy thing. Now another thing is apply the Routh-Hurwitz method to determine the values of k that make the system stable. For the given system is s to the power 5 plus 13 s to the power 4 plus 54 s cube plus 82 s square plus 60 plus k whole into s plus 3k is equal to 0. Yes, that is the thing I already mentioned on the very first slide to you people. for the conditional stable system. Yes, with the depending value of k, we can speak that system is stable, else it is unstable. So that's why this is the actually conditional stable type of example. So similar fashion, our first job, we have to construct the Routh table starting from s to the power 5 onwards, s to the power 5 to s to the power 0 columnize, then substitute the alternate coefficients of that on the very first two rows, that is 1, 54 and 60 plus k will be the first row, then 13, 82 and 3k will be the second row. Successively s cube row generates 47.7 and 60 plus 0.79k. S to the power 2 is 65.6 minus 0.212k and 3k. S to the power 1 is 3940 minus 105k minus 0.163k square by 65.6 minus 0.212k, and s to the power 0 is 3k. So according to the Routh-Hurwitz criteria, we know if the system becomes stable, then enter elements of the first column of Routh array must be positive. So we will start from one by one. So 65.6 minus 0.212k must be greater than 0. That's why we can speak k is less than 301. That is available on the s to the power 2. Now for the s to the power 1 row, if I am focusing that 3940 minus 105k minus 0.163k square should be greater than 0, that generates k should be less than 35. And when I am speaking s to the power 0, that generates k should be greater than 0. So what will be the condition for k by which the system becomes stable? So the value of k that makes the system become stable is k should lies between 0 to 35. And you may speak, sir, you have shown when k is less than 309, that is also available. Yes, I can accept, but if I am taking more than value of 35, that is for the second s to the power 1, then that row, the 36 means that row becomes negative. So to make the system stable, our ranging of k should lies between 0 to 35. This is the optimal solution. Now applying Routh-Hurwitz method to check the system stability of a system whose characteristic equation is given by delta of s is equal to s to the power 5 plus 2s to the power 4 plus 3s cube plus 6s square plus 5s plus 3. Generate the Routh table as follows, that is already see starting from s to the power 5 onwards, s to the power 5, s to the power 4, then s to the power 0, then alternate coefficients on the very first two rows, that is 1, 3, 5, then second row is 2, 6, 3. After restricted multiplication, s cube row contains very first element is 0 and rest element is non-zero, so that is 0 and second element is 7 by 2. So Routh stability criteria breaks down to replace, to avoid, because if I am dividing that element on the s to the power 2 row, that generates infinity. So on that occasion we can replace that 0 by infinitesimally small element, that is epsilon. So on after replacing 0 by epsilon, then as usual multiplication procedure will be going on, that generates s to the power 2 row is nothing, that is 6 epsilon minus 7 by epsilon, and another element is 3, and s to the power 1 row is nothing, 42 epsilon minus 49 minus 6 epsilon square divided by 12 epsilon minus 14, and s to the power 0 is 3. Now interpret the Routh table to tell how many closed loop system poles are in the right half plane. To begin the interpretation, we must assume a sign positive because we don't know what is the value of epsilon. So both cases should be considered. We must assume a sign positive or negative for the quantity epsilon as illustrated in the Routh table. See here. Obviously I am not disturbing the actual element, so I am focusing on the first column of the Routh array that contains, first column is 1, 2 epsilon, then 6 epsilon minus 7 by epsilon, then 42 epsilon minus 49 minus 6 epsilon square divided by 12 epsilon minus 14, then 3. And see, this 3 is matched already, this 3 is matched. Okay, so here 3 is the coefficient of s to the power 0. Now see, at first I will take epsilon positive, then epsilon negative. When I am taking epsilon positive, the first two row epsilon positive and negative does not bother. The third row, that is s cube row, contains epsilon positive means it is positive, epsilon negative means it is negative. S square row When it is epsilon positive, a square row generates negative. When it is epsilon negative, a square row generates positive. S to the power 1 row, when epsilon positive, S to the power 1 is positive row, and when epsilon negative, S to the power 1 row is also positive. Then S to the power 0, because there has no epsilon term, that's why whether it is positive or negative, that row remains positive. So that is the actual inference. So interpret the route table to tell how many closed loop system poles are in the right half plane. There are two sign changes in the left column, therefore Q of S has two right half poles and hence it is unstable. And you may ask me, sir, how you are predicting? Because see, already when I am taking epsilon positive, see, S cube row is positive, whereas S to the power 2 row is negative. Again S to the power 1 row is positive. So positive to negative, then negative to positive. Otherwise, if I am taking S to epsilon is negative, S to the power 3 row is negative and S to the power 2 row is again positive. So S to the power 4 to S to the power 3 is negative, S to the power 3 to S to the power 2 is positive. Obviously, either of the two ways, it will become unstable because two sign changes have occurred. Okay, that's why we can speak two roots lying on the RHP of the S plane, that is right half plane. Now another problem, let us find the stability of the control system having characteristic equation S to the power 5 plus 3S to the power 4 plus S cube plus 3S square plus S plus 3 is equal to 0. Verify the necessary condition for Routh-Harvey stability, step 1, and all the coefficients of the given characteristic polynomials are positive, so the control system satisfies the necessary condition. Now the thing is, see, what is the interesting phenomena will occur for this problem. See, form the Routh array for the given characteristic polynomial. The row S to the power 4 elements have the common factor 3. That's why, see, after making Routh table S to the power 5 to S to the power 0 C, and after substitution of the two successive rows, that is 1 1 1 on the first row, and the third row is, second row is 3 3 3, that means I am taking common 3, that is it is 1 1 1. Then S cube row contains all the row elements are 0. So we can speak Routh stability criteria breaks down, because previously we see only one element was 0, now entire row is 0. So how can I overcome for this problem? So all the elements of the S cube row are 0, so write the auxiliary equation A2 of S of the S to the power 4, because that condition is, if we are obtaining any row for a Routh array is entirely 0, then subsequently you have to construct an auxiliary equation just above that 0 entire 0th row. S to the power 3 row is containing all the elements 0, then we will focus on the S to the power 4 row. So the auxiliary equation is nothing, alternate coefficient fashion, that is A of S is equal to C. Coefficient of S to the power 4 is, I am taking 1, that is 1 into S to the power 4, or then S cube will not come, alternate, that means coefficient of S to the power square is, S to the power 2 is 1, so S to the power 4 plus S to the power 2 plus coefficient of S to the power 0 is also 1. Then we have to differentiate this expression with respect to S, that is dA of S by ds, that is 4S cube plus 2S. Then we will replace this coefficient of S cube and S to the power 1 on that place, because see here I am highlighting S cube row that contains the elements will be 4, another is 2. I am taking common 2, that's why 4 is making 2 and 2 is making 1. Then as usual multiplication is going on. S to the power 2 row contains 0.5 and 1, S to the power 1 row contains -3, and S to the power 0 is contain 1, that is matched. S to the power 0 is contain matched. See, that is 3 already, because already I am taking common, that's why it is coming 1. If I am not taking common, then it is coming 3. So in this occasion, two sign changes have occurred from S to the power 2 to S to the power 1, one sign change, and S to the power 1 to S to the power 0, another sign change. That's why we can speak system is unstable and two roots lying on the RHS of the S plane. These are the respective assignment for you people. Determine the stability of the characteristic equation S to the power 5 plus S to the power 4 plus 2S cube plus 2S square plus 3S plus 5 is equal to 0. And determine the stability of the again given characteristic equation S to the power 6 plus S to the power 5 minus 2 S to the power 4 minus 3S cube minus 7S square minus 4S minus 4 is equal to 0. Then determine the values of K and B so that the system whose open loop transfer function is G of S is equal to k into s plus 1 divided by s cube plus b square plus 3s plus 1 oscillates at a frequency of oscillation of 2 radian per second, assume emittive feedback. Then number 4 is determine the condition of stability for the systems whose characteristic equation is given by s to the power 4 plus 20 s cube plus 224 s square plus 1240 s plus 2400 plus k is equal to 0, and k obviously belongs to real quantity. Also determine the value of k which will cause sustained oscillation. Find the frequency of oscillation. Here answer is k is equal to 7644, frequency omega is 7.9 rad per second, and these are the respective references. Already I told you I am taking help from these books, and that's all for today.